Okay, 4.2 is about the least squares regression line, which is the best fit line for the data. So in 4.1, right, we determine whether or not two variables exhibited a linear correlation. And if they do exhibit a linear correlation, then you might want to know, okay, so then what is the equation for the line that describes that relationship? So one way that we could go about finding the equation for the line would be to draw a scatter plot, pick 2 points from the data that appear to have a good fit for the data, and then find the equation for the line that goes through those 2 points. And if you wanted to do that, right, you could tie in your old algebra skills from your high school days or whatever, and recall that we usually use the letter m to represent slope. And the slope m of a line through 2 points, x1, y1, and x2, y2 is y2 minus y1 over x2 minus x1. I'm not actually going to do any examples because you should be experts at this. You should know how to find the equation for a line, and if you don't, then shame on you. But anyway, you know, this is the slope of the line, and then the point slope form is y minus y1 equals m times x minus x1, right? Where m is the slope, and x1, y1 is a point on the line. And then you plug the stuff in, and then you do some manipulations, and you get the slope-intercept form, which is y equals mx plus b. Now, here's the important part. Well, I mean, it's all important, right? But here's what I really want to help you remember, right? When you end up with an equation that looks like y equals mx plus b, m is the slope, right? So m is the slope, this is the slope. The thing you're multiplying x by is the slope, and b is the y-intercept, right? It's the y-intercept. So that's the place where the graph crosses the y-axis. Okay? So in general, this is the equation for a line. And when we go to look for a best fit line, we're looking to get something like this. Now, if we just eyeball it, if we just pick 2 points and then we go through all this stuff to get our line, is that going to be the best fit for the data? Probably not, right? Probably not. Not if we're just eyeballing it, you know, because we're human. So probably just eyeballing it is not going to be the way to get the best fit. What do we even mean by best fit? Well, by best fit, what we mean is that we want the line that we draw to be on average closest to all of the values. So the line that we draw is going to be the line that minimizes the distance between the line and the points that we're supposed to be modeling with the line, right? That's the idea. And so we want a line that our data is closest to as a whole, or on average, right? And we're going to call this the best fit line. So how do we find the best fit line? Well, you take a course in linear algebra, which is a course that you would take after completing the calculus series, right? But you take a course in linear algebra to find out how to determine the best fit line. And then once you have your strategy that comes from linear algebra, then you do some gnarly calculations. And what you would end up with, I'm going to just give you the results because most of you haven't had linear algebra. In fact, I would venture to say all of you, none of you have had linear algebra yet. But you would end up here. You would see that the best fit line for the data is something called the least squares regression line. It's called least squares because it's the line that minimizes the square of the distance between the point and the line. So in other words, I'm thinking of like a scatter diagram, right? That kind of looks like this, and well, this is kind of bad, but the distance between the point and the line is that right there. And then here's another, maybe we'll call that distance 1, and maybe we'll call this one distance 2, and maybe we'll call this one distance 3, right? So you have all these distances, and that's actually a really bad drawing, but I think hopefully you get the idea, right? You get all these distances, and then you want to minimize, you want to draw the line so that it minimizes these distances, right? The average of those distances. That's essentially what the least squares regression line does. So least squares regression line is we read this symbol y hat. So we say y hat equals b1x plus b null or b naught or b0, whatever you want to call this thing. So y hat equals b1x plus b null, where b1 is our linear correlation coefficient from 4.1 times the ratio of the standard deviations of the y group and the x group. And then b null is the average of the y's minus b1 times the average of the x's. It's, oh man, it's tedious, right? It's like if you wanted to compute this by hand, first of all, just computing r by hand it takes forever. And then you have to do some more work on top of that to get b1 and b null. It's just a lot of work. So once again, we're not going to do all the work. We're going to let Statcrunch do that for us, okay? So in Statcrunch, to find the least squares regression line, you go to Stat, and then Regression, and then Simple Linear. The main takeaway, the main two things I want you to take away from our discussion on this first page, though, are these two things. First of all, to remind you that the thing you're multiplying by x is the slope of your line, and the thing that you're adding is the y-intercept of the line. So that's the first thing. And then the second thing that I really want you to walk away understanding is that this line that we're coming up with, the least squares regression line, is the best fit line. It's the line that minimizes the distance between the line and the points that the line is supposed to model. Okay, so you can't get any better than the least squares regression line, okay, in terms of fitting your data. Of course, this only applies if you have a linear correlation in the first place. If you don't have a linear correlation in the first place, then you have no business trying to find the best fit line, because there isn't a linear correlation between the data, okay? So let me walk you through a few examples. Here we have the data from 4.1 example 1, okay? Let's find the best fit line, or in other words, the least squares regression line for the data. So to do this, we go to Stat, Regression, and then Simple Linear. And of course, before you even do all of that, you have to enter the data into Statcrunch. Once again, I've taken the liberty of just having the data already in there, okay? So this is example 1, and then we'll do a couple more examples with these data sets. But with this example, let's find the linear correlation coefficient. Go ahead and give the video a pause and enter the data if you haven't done so already, so that you can follow along with what I'm doing. But let's go, so let's do this. So we're gonna go Stat, Regression, Simple Linear. And then we need to compare the number of absences and the final grade. And the rest of the stuff, just leave it on its default setting. Go ahead and just hit compute. And you get a whole bunch of stuff that you're not going to understand right at this moment. However, later on in the course, you'll understand what we mean when we talk about p-values and stuff like that. But what is important for you to look at is, well, there are a couple things. First of all, notice that this table gives you the correlation coefficient. So in 4.1, we talked about how to get the correlation coefficient, but we got it differently. We went to Stat, Summary Stats, Correlation, and then we got the correlation coefficient this way. But you'll notice that it's the same number, right? Negative 0.944-ish, right? So, so going to Stat, Regression, Simple Linear, that's what gives you this stuff. And so it gives you the correlation coefficient and then some. It also gives you more information. Another thing to point out on this page is that here is your best fit line, right? This is the least squares regression line. Final grade was supposed to be our y variable, and number of absences was supposed to be our x variable. So another way to write this would be to say y equals 102.49 whatever minus 3.62x, okay? And personally, I don't like it written that way. I like it when it's written in the form y equals mx plus b, so I like it when this term comes first. But it's not wrong to write it backwards. It's just backwards in my opinion. But anyway, another way to see the same thing is if you scroll over to the next page. So you come down here to these arrows, scroll over to the next page, and you'll see that it also draws a scatter plot for us together with the best fit line superimposed over that scatter plot. Now, if you'll take your cursor and hover over that best fit line, then it gives you the least squares regression equation for that line. So that's another way to see the least squares regression equation, okay? So I'm gonna write that down. I'm gonna rewrite it. I'm gonna rewrite the order though. So I'm gonna say y hat equals negative 3.62x plus 102.49. So I'm rounding to 2 decimal places, okay? So here's what I've written down. Y hat equals negative 3.62x plus 102.49. There's my least squares regression line. Okay. Now, part B says, interpret the slope and y-intercept if appropriate. Okay. Well, first of all, what is the slope of this line, right? So the slope is the thing that you're multiplying your x variable by, right? So there's the slope in this case. And even if we wrote it in the other order, right? This is the order that Statcrunch gave it to us. It wrote it like this. But negative 3.62 would still be our y-intercept, right? Or sorry, our slope. This would still be our slope. It's always the number that you're multiplying by x, right? That's your slope. So m is negative 3.62. Well, it's approximately negative 3.62. And the y-intercept, right? The y-intercept, b, is approximately 102.49. Now, how do we interpret this? Looking at the scenario, we were comparing number of absences to final grade, and we're getting a slope of negative 3.62. You can think of that like negative 3.62 over 1. So, in other words, for every increase in absences, there's a decrease in your grade of negative 3.62%. Okay, right? This is rise over run. So this is y over x. So it's grade over absences, right? So it's the decrease in grade for every increase in absence, right? So so as far as the slope is concerned, right, for every additional day of class missed, the final grade decreases by negative 3.62%. Okay? So there's the slope. The y-intercept, 102.49. Now, the y-intercept is where the graph crosses the y-axis, right? So our graph might look something like this. That point right there, we're saying is 102.49. Now, that's the y value, 102.49. What's the corresponding x value? Well, the corresponding x value is, of course, 0, right? So in other words, the y-intercept represents what would happen if a student didn't miss any class. So if a student misses 0 classes, then they can expect to end the class with a grade of 102.49%. Probably not, right? Probably not. That's the interpretation of the y-intercept. Now it says, interpret these things if appropriate. And the reason it's saying if appropriate is because it's not always appropriate to interpret the y-intercept, and this is a clear case of that, right? You're not going to get more than 100% in a class. So unless there's a lot of extra credit in the class, which is possible, I guess, for some some instructors. But most of the time, you're not going to be able to get above 100% in a class. So obviously, this is inappropriate. It's an inappropriate thing to interpret. Now, the reason that it's inappropriate is because you'll notice that your original data, the smallest observation was 2 and the largest observation was 15. So those are our restraints. It's like we're really not allowed, we're really not justified to make any predictions that fall outside of that range, right? So we can't really predict the final grade of a student who missed class less than 2 times or more than 15 times, right? Because our model is not based on information that includes values outside of that range. And so in this case, right, since our y-intercept happens when x is 0, it falls outside of the range of appropriate predictions, right? So it's not appropriate to interpret the y-intercept in this case. So y-intercept, not appropriate to interpret. Okay, it's not appropriate to interpret it. But that's how you would interpret it. If it were appropriate to interpret it, you would say that the interpretation would be if a student misses class 0 times, they'll get 102.49% in the class, right? That would be the interpretation. Okay, then part C. What would you predict the final grade to be for a student who missed class 10 times? See, 10 falls within our restraints. So it's appropriate to go ahead and make a prediction about the grade they would get if they missed class 10 times. And to make that prediction, we use our least squares regression equation, right? We say, well, y hat would be negative 3.62 times 10, right? If they miss class 10 times, plus 102.49. So let's see. Whoops. Okay, so I'm coming up with 66.29. So that would be their grade in the class, 66.29%, right? That would be their final grade in the class. And by the way, I'm giving you percentages as my answers, like here and here, right? Decreases by 3.62%, only because we're talking about grades, right? Obviously, these final grades in the class are their percentage in the class, right? So this student got 74% in the class. You wouldn't necessarily turn everything into percentages. Okay. So that's that. Now, when predicting a y value given an x value, we only use the best fit line if, in fact, there is a linear correlation between those variables. As we saw in section 4.1, I don't know if it was example 4, because I think I've changed the notes since I wrote this. Was it example 4? No, it was example 5. So as we saw in 4.1 example 5, not all variables have a linear correlation. And so when the correlation coefficient R indicates no linear relationship between the variables, then it's not appropriate to even find the least squares regression line, let alone to use it to make a prediction. In this case, right, the best prediction you can make is to just say that the predicted value for y is going to be whatever the average of all of the y's are, right? That's the best we can say for our prediction, okay? Since y bar is sort of the typical value, it's supposed to be the typical value, the mean. Okay, so with that in mind, let's look at a couple more examples. This one says, an engineer wanted to determine how the weight of a car affects gas mileage. The following data represents the weights of various domestic cars and their miles per gallon in the city for the 2008 model year. So we have their weight. It doesn't say what the unit of measurement, but I'm assuming pounds probably. So this is their weight in pounds, and then the miles per gallon that they get. So we're asked to do a whole bunch of things. Draw a scatter plot, find the linear correlation coefficient, determine if there's a linear relationship. If there is, find the least squares regression equation, interpret, this has just so many typos. Interpret the slope and y-intercept if appropriate, and then use the regression equation to predict a car's miles per gallon if it weighs a certain amount. So let's do all that stuff. First of all, you've got to get the data into Statcrunch. So if you haven't done so already, pause the video and get the data into Statcrunch. I've already entered it, and I don't know if I double checked to see if I got it all in there correctly, but I think it's looking pretty good. 26, 17, 20, 25, looks good. Okay, so let's do all the stuff they asked us to do. First of all, if we want to scatter plot, we can go to graph scatter plot. And we want to compare weight and miles per gallon. Whoops. If we want the linear correlation coefficient, we can go to stat, summary stats, correlation, and compare weight and miles per gallon. That looks like a pretty strong negative linear correlation, right? And then if we want the least squares regression equation, then we can go to stat, regression, simple linear, and then we can compare weight and miles per gallon. And this one gives us not only the least squares regression equation, but it also gives us the correlation coefficient that we already got, as well as a scatter plot. So really, you don't even need to do these first two things because they're all done when you find the correlation, or when you find the least squares regression equation. Okay, but let's write some stuff down, right? So our correlation coefficient, R, is approximately negative 0.959. And so, of course, that means the absolute value of R is positive 0.959. And to determine if there's a linear relationship, we need to compare this to a critical value. So I'm going to look at that chart again from 4.1, right? The critical value chart from 4.1. And here I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 observations, right? 10 observations. So n equals 10. Right, so for a sample size of 10, the critical value is 0.632. So that's the number that I have to beat, is 0.632. And I've done it, right? That is definitely bigger than the critical value. So I'm going to say for n equals 10, critical value is 0.632. Since 0.959 is greater than 0.632. This is absolute value of R, and this is the critical value, right? Since the correlation statistic is greater than the critical value, there is it says determine the type and direction. So we need to say if it's positive or negative. And since R was negative, we're going to say there's a negative correlation, right? So there is a negative linear correlation. That makes total sense, right? It's like the heavier the car, the less miles per gallon it's going to get. That just makes intuitive sense. So of course there's a negative linear correlation. And then part C says find the least squares regression equation. So least squares regression equation is right here. Another place you can see it is to hover your mouse, hover your cursor over that best fit line right there. So I'm going to write it down. I'm going to say y hat is approximately negative 0.007x plus 44.4. Okay, so that's what I've written. That's what I've written down there. Now part D says, interpret the slope and y-intercept if appropriate. Well, the slope is negative 0.007. Slope is rise over run. So it's y over x, right? So it's miles per gallon over weight. So if I'm thinking of this as negative 0.007 over 1, then what I'm thinking, right, this is miles per gallon over weight. So for every increase, for every 1 pound increase in the weight of the car, there's a negative 0.007 decrease in miles per gallon. Ooh, okay. Let me do this again. So for every pound increase in the weight of the car, there's a decrease in miles per gallon of negative 0.007, right? So for every pound of weight, there's a negative 0.007 decrease in miles per gallon. That's kind of a weird thing to think about, but imagine if you had 100, right? 100 down here, then you would move the decimal a couple times, better yet, 1,000. So if we added 3 zeros down here, then you would move the decimal 1, 2, 3 times. And what that would mean is that for every 1,000 pounds of increase in weight, there's a decrease in 7 miles per gallon, right? So the car gets 7 miles per gallon fewer for every additional 1,000 pounds of weight that it has to carry, right? So that's the idea there. Okay. And then part E says use the regression equation to predict. And so that's the slope, right? That's the slope. What about the Y-intercept? Well, the Y-intercept, B equals 44.4. So that means that if a car weighs 0 pounds, then it would get 44 miles per gallon. That's pretty meaningless, right? So not appropriate. It's not appropriate to interpret, right? It would mean if a car weighs 0 pounds, then it gets 44.4 miles per gallon, right? So clearly not appropriate to make that interpretation. This falls way outside of the constraints that we have here, right? The smallest car was, I think, the Ford Focus. No, the Dodge Neon at 2,580 pounds. So 0 pounds is way outside of the scope of our model, right? Okay, and then part E says, use the regression equation to predict a car's mile per gallon if the car weighs 3,500 pounds. So again, we're going to use this regression equation from part C. We're going to say, if the car weighs 3,500 pounds, how many miles per gallon does it get? Let's see. $19.9. So that comes out to 19.9 miles per gallon. So if a car weighs 3,500 pounds, then it gets 19.9 miles per gallon. That would be our prediction. Okay. So that's how this works. Let's look at one more example, because I want to give you an example of something where there isn't a correlation or where there isn't a linear correlation. So spoiler alert, right? This one's not going to be, there's not going to be a linear relationship between these variables. But let's look at the example, right? So it says, the following data represent the total compensation for 10 randomly selected CEOs and the company's stock performance in 2009. All right? So here's their compensation in millions, right? So the CEO of Boeing made $19.44 million in 2009. And the CEO of Abbott Laboratories made $26.21 million in 2009, right? And then here's their stock return, right? So this company lost money on the stock market, right? And this company made a whole bunch. I don't know what middle B is. Actually, I don't know what most of these things are. Abbott Laboratories, I have no idea. Anyway, oh, maybe not most. I mean, I know Kraft Foods and Sara Lee and Boeing and what's Exelon? I don't know. It doesn't matter. Let's see if there's a correlation. Now, part A says, one might think that a CEO has a larger salary if the company has a larger stock return, right? They might think that because if a company makes more money, then it can afford to pay its CEO more. Okay, that makes sense. Based on that assumption, which variable would be the explanatory and which is the response? Well, we think if the company has a good stock return, then it's going to be able to afford to pay the CEO more money. So we're thinking that the stock return explains the compensation, right? So we would say the stock return would be the explanatory variable. The stock return would be the explanatory variable, and the compensation would be the response. Hold on. Okay, I'm gonna mute this for a second. My daughter has something urgent to tell me. All right. Sorry about that. So, so we're thinking the explanatory variable is the stock return, and this is kind of misleading because of the way that it's set up here. But we're thinking that this is the explanatory variable x, and that this is the response variable y. Now you could argue the other way around pretty easily. You could say something like, well, if a company pays its CEO more, then that's probably because that CEO is really good at what he or she does. And if the CEO is really good at what he or she does, then the stock return for the company is going to be larger, right? So you might think the compensation drives the stock return. You could argue the other way around, but in this particular example, we're assuming that that the stock return is going to drive the compensation. Okay, so that's that. Now we're asked to draw a scatter plot, get the correlation coefficient, make some predictions. So let's do all that stuff. Once again, if you have not yet entered the data into Statcrunch, go ahead and pause the video and do so that you can follow along with what I'm doing. But I went ahead and worked ahead and just entered it already. So, so if I want the correlation coefficient and a scatter plot and stuff, then I might as well just go ahead and compute the least squares regression line, so that, because it does all of those things for me already. So I'm just going to go ahead and compute the least squares regression line by going to stat, regression, simple linear. And then I want to compare stock return to compensation. And notice the order that I'm doing this in, right? Stock return, we said, would be our x variable. So you need to choose stock return for your x and compensation for your y, right? Okay, then I hit compute. And there's our correlation coefficient. Okay, if you're following along, then I'll let you kind of look at this. I'm going to mute this again for a second. I've got to close this door because my daughter left it open when she left. Okay, that's a little better. You can probably still hear them in the background arguing, but anyway, so there's our correlation coefficient. Here's our scatter plot. Ooh, yeah, you can see the dots are kind of all over the place, right? Our correlation coefficient is not strong at all. So let's write that down, right? So R is approximately negative 0.206. that means that absolute value of R is about 0.206. And again, I think we have 10 observations here, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So for n equals 10, our critical value, we just found this on the previous problem. For n equals 10, our critical value is 0.632. Since 0.206 is less than 0.632, right? This is absolute value of R, this is our critical value, right? So remember, our correlation coefficient needs to be bigger than the critical value, and here it's not, right? It's smaller than our critical value. So since this is the case, there is not a linear correlation. Right? There's not a linear correlation between the variables. So when they ask us to do like what they're asking us to do in parts D and E, right? Part D says, what would the predicted compensation for a CEO whose company had a 41% stock? What would be the predicted compensation for a CEO whose company had a 41% stock return? We would just say, since there's not a linear correlation, it doesn't make sense to use the least squares regression line to make this prediction. The best we can do is to say, is to just look at the average compensation, right? We would just say, well, our prediction, Y hat, is that they're going to make the average amount that a CEO makes. Okay, that's the best we can do because we did not find a correlation between salary and stock return. So for that matter, your answer to part E is going to be the same, right? What would you predict? What would be the predicted compensation for a CEO whose company had a negative 2% stock return? Same thing, because there's not a correlation between stock return and compensation. So the best prediction we can make is to just say that they're going to make the average amount that a CEO normally makes. Now, what is that average? We can find that pretty easily. We go stat, summary stats, columns, and then we want the average compensation. So I'm going to click compensation, mean, and hit compute, and there you go. All right, so 16.88 million, it seems. Same here. Okay, that's pretty interesting. That's kind of interesting. Because we think of business, I mean, this data could be made up, right? Like, so you should take this with a grain of salt. I'm not saying that this is true, but suppose that it is true for a second. It's like, we often think of business as sort of cutthroat, and like, if you're not doing a good job, you lose money, you'd be fired by, you know, the stock, by the shareholders and all this stuff, but that's not what this data is saying, right? This data is saying there's no relationship between the stock. So this company that earned a 41% stock return, the CEO made the same amount as this guy who lost money. So anyway, that would be very interesting if it were true, right? It would make you think differently about CEOs maybe. But here's your homework assignment. You can use Statcrunch on all of it. If there's anything that says do this thing by hand, just ignore that. Use Statcrunch. The problems are way too tedious to do by hand. And we'll see you in 7.3.